I'll start with a small recap of what we did in last class. Okay, first thing we saw is the theorem that says that conditioning reduces entropy. That is, h of x given y is less than or equal to h of x with equality if and only if x and y are independent. And we saw an example to calculate h of x given y. And we also showed that h of x given y is less than or equal to h of x. Then using that theorem, we gave an independence bound, a bound on the entropy called the independence bound, given a set of random variables x1 to xn with a joint probability distribution p of x1, x2, etc. to xn. The joint entropy h of x1 to xn is less than or equal to sum of the individual entropies, summation h of xi, I is equal to 1 to n. Then we moved on to some important inequalities in information theory. The first inequality is log sum inequality. And this log sum inequality doesn't really have anything to do with entropy, but it has the same form. It has a log in it, so it's very useful uh, when we are manipulating entropy information, etc. But this works for any general setting. And the theorem says that for any non-negative numbers a1, a2 up to an and b1, b2 up to bn, so two sets of non-negative numbers, summation of ai times log of ai over bi is greater than or equal to summation of ai multiplied by log of summation of ai divided by summation bi, with equality if and only if ai by bi is a constant. The convention we follow is as usual, 0 log 0 is 0, 0 log non-zero quantity by 0 is infinity, 0 log 0 by 0 is 0. And we can apply that log sum inequality and show that the relative entropy is a non-negative quantity. We had seen a different kind of proof earlier, uh, but we can also prove this using the log sum inequality. D of p parallel q is greater than or equal to 0 with equality if and only if p and q are the same distribution. Then we proved a theorem that says that relative entropy is a convex function and it is convex in the pair of distributions. That is, if you have a pair p1 q1 and another pair of distributions p2 q2, then the relative entropy between the mixed distribution lambda p1 plus 1 minus lambda p2 relative to lambda q1 plus 1 minus lambda q2 is less than or equal to lambda times d of p1 parallel q1 plus 1 minus lambda times d of p2 parallel q2, where lambda is some number between 0 and 1. So in the pair PQ, the relative entropy is a convex function. Then we use that fact to prove that the entropy function is a concave function in the probability distribution, because the entropy h of p can be written as log of cardinality of x minus d of p parallel u, which we saw in a previous class, where u is the uniform distribution. Since d, the relative entropy, is convex, minus d is concave, and log of cardinality of x is a constant function. So by adding a constant, you don't change the concavity or convexity of the function. So h of p has the same property as minus d, which is concave. Then we went on to examine the concavity or convexity of mutual information, and we saw that if you have two random variables x and y with a joint distribution p of x comma y, which you can write using basic probability as p of x times p of y given x. If you fix one of the probability distributions, if you fix p of x and then you vary p of y given x, then the mutual information I of x semicolon y is a concave function, is a convex function of p of y given x. If you fix p of y given x and vary p of x, then the mutual information is a concave function of p of x. Then we moved on to data processing inequality. And to understand data processing inequality, we need to know a few terminologies. So we define a few quantities. First definition is the meaning of a Markov chain. We say that three random variables x, y, z form a Markov chain in the order x arrow y arrow z. So the order is important here. If the joint PMF p of x by z is can be written as p of x times p of y given x times p of z given y. So usually the third term p of z given y should have been p of z given x comma y, but for a Markov chain given y, z is independent of x. And we saw some simple consequences of this definition, what happens for a Markov chain. And one consequence is that given y, x and z are independent. So this definition only says p of z given x comma y is equal to p of z given y, but that leads to the fact that p of x comma z given y is equal to p of x given y into p of z given y. So x and z are conditionally independent given y. Then if z is a function of y, then x, y, z forms a Markov chain. So once we know what a Markov chain is, we can derive an inequality called the data processing inequality, which says that if x, y, z form a Markov chain, then mutual information between x and y is greater than or equal to mutual information between x and z. What it means is that if x, y, z form a Markov chain, then whatever information about x you can get from z is always less than the information you can get from y about x. That notation gives you the ordering. So if you write that in that notation, then it means that given y, the probability of z given y is equal to probability of z given x comma y. Yes, yes, that's what it means. So distribution p of z given y gives a distribution of z given y, right? For different values of z and y. The distribution of z, conditional distribution of z given y, that does not depend on what value x takes. That's what it means. Yeah. Just by knowing the value of y, uh, you can give a probability distribution for z. That's all that z uh, depends on. So we saw in a previous At the beginning, we saw, so this gives you a distribution, right? Uh, this gives you a joint distribution, and you can find the marginals and also the conditional distribution from this. Uh, so given y is equal to 1, probability distribution of x is this thing normalized. So if you normalize it, it will become 0 and 1. And normalize, I mean divided by the sum of the probabilities. So that means given y is equal to 1, probability x is equal to 1 is 0, probability x is equal to 2 is 1, this distribution. Similarly, given y is equal to 2, you have to normalize this. You'll get half and half. That is, given y is equal to 2, probability of x is half, and probability x is equal to 1 is half. Probability x is equal to 2 is also half. So when you have three random variables, if it forms a Markov chain, you can give this kind of probability distribution between z and y, and the values won't depend on the value of x. Otherwise, in general, if you have three random variables, uh, when you expand it out, yeah, you'll get you can so your probability that z takes a particular value only depends on what value y is taking, not what value x is taking. So from that we can prove that if it's if you have such a Markov chain, then the mutual information that this random variable z contains is always about x is always less than or equal to the mutual information that y contains about x. In particular, if you apply this to a function, say if you say z is a here we saw that if z is a function of y, then x, y, z form a Markov chain. So then you can apply the data processing inequalities to say that I of xy greater than or equal to I of xz, which means by a function we are actually trying to process a data. Any type of data processing that you do using y or any type of manipulation you do using y is a function, right? So no matter what manipulation you do on y, um, you can't get any more information about x than what you can get by directly observing y. That's what the data processing inequality says. So processing this random variable y won't give you any more information on x than what y already gives. And this thing is this equality holds only if x and y are I of x and y given z is equal to 0. That is, given z, y does not give you any more information about x. Then you can say the mutual information that y contains about x is equal to the mutual information that z contains about x. So here is a corollary. The corollary says if z is a function of y, then x or z forms a Markov chain. So I of xy is greater than or equal to I of x g of y. Now we had seen earlier that conditioning reduces entropy, but for information, it's only true if the variables x, y, z form a Markov chain. So I of xy is greater than or equal to I of xy given z. So you're conditioning on z. So the conditioning is reducing mutual information, but this only happens if x, y, z form a Markov chain. For entropy case, h of x given y is always less than or equal to h of x, regardless of what x and y are, what type of random variables they are. But in this case, I of xy given z is less than or equal to I of xy only if xy z form a Markov chain. It's not an if and only if statement. It says that if xyz forms a Markov chain, I of xy greater than or equal to I of xy given z. If it's not a Markov chain, it might be greater or lesser. Then we calculated all these quantities and showed that, yeah. So I showed an example where um, I of xy given z is actually greater than I of xy. So I took three random variables x, y, z, which don't form a Markov chain, and here we see that I of xy given z is actually half a bit, but I of xy is 0. So I of xy given z is actually greater than I of xy. That's what we saw in last class. So in today's lecture, we'll see two topics. Sufficient statistics and Fano's inequality. So after this, the chapter number 2 is completed from Thomas and Cowell book. So for next 3-4 lectures, I will solve a few problems from the textbook. After that, for some 3-4 lectures, I will do chapters 3 and 4, parts of it, not entirely. I'll see how much I will do. And then I'll conclude this course. Maybe I'll solve a few problems on those topics also. Next semester, uh, sometime after April or sometime after May, I will offer the second part of the course where I will do the applications uh, related to communication. So, compression and channel capacity. So this time I won't cover those topics. These are just basics which you can use for any field. These are not really restricted to communication, but the applications will be only for communication. So I'll do that as a different course in the next semester. Okay, we'll start with sufficient statistics. So this is something that usually comes up in estimation, detection and estimation. Again, that is also something you would study in the ECE. Uh, so suppose you have a family of PMFs indexed by a random variable theta, and X is a sample from a distribution that belongs to this family f theta of x. That is, you have a random variable x. That random variable can be drawn from different types of distributions. So, which distribution x takes itself is decided according to some parameter that we call theta. For example, if you have a coin toss, so you're tossing a coin. The random variable takes the value 1 if you get a head, it takes the value 0 if you get a tail. The distribution depends on probability of x is equal to head and probability that x is equal to tail. If that is unknown, if it's if that itself is a variable, so when we usually say such a binary random variable has is equal to 1 with probability p and equal to 0 with probability 1 minus p. When we say that, we usually say it's the p is fixed. But suppose p is unknown, you don't know, then depending on the value of p, you have different distributions, right? Each value of p gives you a different distribution for the coin toss. So that's what I mean by a family of PMFs. So there are multiple distributions that x can take depending on the value of theta. Then you have some function of x, say t of x, which is a function of this sample. And that is called a statistic. So when we are talking about sufficient statistics, that's what the statistic is. It's a function on the sample. Since it's a function, then theta x t of x forms a Markov chain. So for any random variables x, y, z, if z is a function of y, x, y, z forms a Markov chain. Yes, is there a question? So that's what I said. It's not specifically for theta x t of x. For any random variable x, y, z, if z is a function of y, then x, y, z form a Markov chain. I can only give you a qualitative explanation. Quantitatively, you would have to. I don't have an example to explain it. Uh, T of x is a function of x, right? So given x, it will be independent of theta, T of x. So suppose you have, yeah, the example would be suppose you have, um, suppose you have x is a coin toss, and you have n coin tosses, x1, x2, xn. T of x is the, let's say it's the uh, sum of all the coin tosses is equal to 1 to n. That is, when you toss a coin, if you get a head, you'll call it 1, and if you get a tail, you'll call it 0. So the number of heads depends only on given the value of x, given what the coin toss was, given the sequence of coin tosses, the number of heads doesn't depend on what the probability of the coin tosses is, right? So that's why it's a function of only x and it won't depend on y, and it depend on theta. Yeah. Uh, I in the example I told you, right? X takes value 1 with probability theta, 0 with probability 1 minus theta if you have a binary random variable. It's a biased coin toss. It's not a fair coin toss. So it can take heads with the different probability and tails with different probability. Yeah, yeah, that's all. If z is some function g of y, then x, y, z is a Markov chain. What do you mean by a function? Yeah, given y, you will get a value of z, right? So that thing, a function takes uh, an input and gives you an output, and the output depends only on the input, all the inputs, right? No, that by definition we are saying if we say it is a function of y, we mean that it is completely it depends only on y. If it's a function of x and y, we will write it as g of x comma y. By writing it as g of y, we mean that it only depends on y. Yeah. And that was of interest to us because we wanted to know that by manipulating y, can we get any more extra information about some other random variable x. And we found out that if there are two random variables x and y, maybe they are related, maybe they are independent, then observing y will give you some amount of information about x. Now, the manipulating this y in any way won't actually give you more information about x. It will at most give the same amount of information of x, or it might give even lesser information about x. So now theta x t of x forms a Markov chain. Then we can apply the data processing inequality. From data processing inequality, we get I of theta comma t of x is less than or equal to I of theta comma x for any distribution on theta. So here if this equality holds, that is if uh, I of theta comma theta semicolon t of x is equal to I of theta semicolon x, then no information is lost, and we say that t of x is a sufficient statistic. So more formally, we'll define it in this way: a function t of x is called a sufficient statistic relative to the family of distributions f theta of x if x is independent of theta given t of x for any distribution on theta. That is, theta t of x forms a Markov chain. So that is how we define a sufficient statistic. And from the previous class, we saw that in the data processing equality, if I of xy, I of xz was less than or equal to I of xy, and that equality will hold only if I of uh, xy given z was 0. So here it will be I of x comma theta given t of x is 0. And that only happens if theta and x are independent given t of x. So it's an indirect way of saying I of theta comma theta colon t of x is equal to I of theta semicolon x. So x is independent of theta given t of x. So why it's called sufficient statistics is that to know about what if the quantity you're interested in is theta, right? Here the quantity of interest is theta, not x. X is some experiment you do. Suppose you have a coin and you are tossing the coin, you don't know the bias of the coin. That is, you don't know what is the probability of heads or tails. You don't know if it's a fair coin or not. And you want to find out the distribution. You want to find out what is the probability that you get a head. So in this case, the quantity of interest is the distribution theta. Then to do that, what you would do, you would usually toss the coins, and after tossing a large number of coins, you will take the relative frequency, right? You'll find the number of heads divided by total number of tosses, and you'll say that is the probability of heads. That's one way of doing it. Then the So about the distribution, this coin toss itself will contain some information. But if you have a sufficient statistic, which is a function of the coin tosses, and if you have a statistics is a function of the coin tosses, and if it is a sufficient statistic, then you only need to know the sufficient statistic to get information about the distribution. That is, whatever information the coin tosses itself will give you about the distribution or the probability mass function of the tosses will be contained in the sufficient statistic. So we'll see that with an example. Before that, I'll go to the restroom and come back. I'll be back in 2 minutes. Okay, let's see the example. So you have a sequence of random variables x1, x2, xn. Each of the xi's takes a value either 0 or 1. And this is an IID sequence of coin tosses. So it's independent and identically distributed. With the distribution being unknown, the unknown parameter theta is the probability that the coin toss results in a head. Given n the number of ones in x1 up to xn is a sufficient statistic for theta. So the number of ones here is nothing but t of x1, x2 given n coin tosses. It is the sum of each of the coin tosses. Of course, here by coin toss I mean the random variable that gives value 1 for heads and 0 to tails. Now, suppose someone tells you that there are k of the tosses resulted in a 1. So in the n tosses, you got k ones. Then the probability that your sequence of random variables was equal to one particular sequence, where each of the small x's belong is either a head or tail. Uh, that is, it is either a 0 or 1. Given that there are k ones in that sequence, is 1 over n choose k if that sequence has k ones, 0 otherwise. So uh, we are talking about a sequence of independent coin tosses, each identically distributed. So for each coin toss, you have probability theta of getting a 1, 1 minus theta of getting a 0. So if someone tells you that there are k ones, that is k of the tosses gave you a heads, what is the probability of each sequence that has k ones? So if this x1, x2, xn is a sequence of random variables, each time this can take a 0 or a 1. X2 can take the value 0 or 1. Each of these can take a value 0 or 1. So once you do n coin tosses, you have a sequence of zeros and ones, right? So it's some sequence 0, 1, 0 something. You have n of these. So there are 2 power n sequences, right? If someone tells you that there are k ones in that sequence, right? Then what is the probability that you got a particular sequence out of all the possible sequences with k ones? Okay, take any one sequence, okay? Let's do it with one example. Let's say there are 5 coin tosses, okay? And I say that k is equal to 3, that is 3 of the coin tosses gave you a 1. So one possibility for this is 11100, right? You agree, right? Yes. Uh, so there are n choose k number of ways of doing that, right? So given out of all those n choose k ways, you select a particular sequence of ones and zeros. What is the probability that you get this particular sequence? Since these are independent, probability that x1 is equal to 1 and x2 is equal to 1 and x3 is equal to 1, x4 is equal to 0, xy is equal to 0. That is probability that this sequence x1, x2 up to xy is equal to 1, 1, 1, 0, 0. Since they are independent, this is equal to probability that x1 is equal to 1 into probability that x2 is equal to 1 to probability that x3 is 1 to probability x4 is 0 and probability that xy is equal to 0, right? But what is probability that x1 is equal to 1? No, I told you, right? Theta is, it's not a fair coin. No. Yes, the probability that you get a 1 itself is theta. Then the probability that you get a 0 is 1 minus theta because you can get only one of two possibilities. And sum of the probabilities of both possibilities must be 1 because it's a probability distribution. So probability that x is equal to 1 is theta. Probability that x is equal to 2, x2 is equal to 1 is also theta because it has the same distribution and it's independent. It's independent and identically distributed. So it's independent of the value of x1. Probability that x3 is equal to 1 is also theta. Probability that x4 is equal to 0 is 1 minus theta. Probability that xy is equal to 0 is 1 minus theta. So this entire probability is theta cube into 1 minus theta square. That's the probability of getting one particular sequence. But for any other sequence that has three heads, let's say 10110, yeah, what is the probability that you get this sequence when you toss the coin five times? Yeah, that is also equal to theta cube into 1 minus theta square. So for any sequence that contains k heads out of n tosses, the probability is the same. So they are equally likely outcomes. So the conditional probability when someone says that you have k one is 1 over the number of uh, possible sequences, right? Because each of the sequences is equally likely. N choose k, and they are all equally likely. So the probability of any one of those is 1 divided by n choose k. That this is only true given xi is equal to k. Otherwise, the probability is theta cube into 1 minus theta square for each of the sequence. But when you know that uh, there are k ones, then the probability becomes 1 over n choose k, which this is not dependent on theta. Regardless of the value of theta, this is true. So this probability that your sequence takes is equal to one particular sequence, that will be some power of theta into some power of 1 minus theta. If you don't know any other information. But if you know exactly that k once must have occurred, then the probability of a particular sequence is zero if that sequence doesn't have k ones. If it does have k ones, then its probability is 1 over n choose k, because all the sequences with k ones have the same probability. So in either case, the probability doesn't depend on theta. So therefore, theta summation of xi is equal to 1 to n, and the sequence of random variables forms a Markov chain. And also, T is a sufficient statistic for theta. So if there is any confusion in this, you should go back and check uh, check your probability notes, maybe, if there is confusion in the probability aspect. And since the recording will also be available, you can rewatch this section later. So the consequence of this is that if you have some um, if you're trying to estimate the probability of some coin, probability distribution of some coin, that is, what is the probability that a coin gives you heads when the coin is you don't know whether the coin is fair or not. If it's a fair coin, it's equally likely probability of heads and tails is equal to half. If it's not a fair coin, then probability of heads is some value theta, which is between 0 and 1. Probability of tails is 1 minus theta. So if you want to estimate what this theta is, then you might have some algorithm that does it by conducting many experiments. So what the sufficient statistic says is, whatever information conducting this n experiments and observing that sequence will give you, the same amount of information is retained if you add all the random variables and store the sum. So the summation of xi I is equal to 1 to n contains all the information that you can possibly get about theta. So you can discard this entire sequence x1 to xn and keep only this summation xi, and that will be enough for anything you want to do to figure out the value of theta. So what happens then is, if you do an experiment with 100 coin tosses, then you will have to store a sequence of 100 zeros and ones, for which you will need one bit for each of the coin toss. So you'll need 100 bits. But if you store only the sufficient statistic, which is the sum of the 100 bits, then that sum can take a value between 0 and 100, which you can store using only 7 bits, because 7 bits gives you 128 possible sequences. So you can encode that and store only 7 bits of information, and that 7 bits of information will give you the same info about theta as x1 to xn does. So that's the use of a sufficient statistic. Okay, we are that is all about sufficient statistics. Next, we go to Fano's inequality. This Fano's inequality is used in a lot of places where you prove negative type of statements. For example, in Shannon's capacity theorem, it says that if it has two parts. It says if the rate of the code is less than the capacity, then you can have codes that give you arbitrarily small amounts of error. But another part is that if the rate is above the capacity, then you can't have vanishing error probability. So the part where it says you can't have vanishing error probability will use Fano's inequality. So the Fano's inequality is used to prove negative statements most of the times. Before that, so what this inequality actually gives is the relationship between the probability of error in guessing x given some under random variable y and the conditional entropy h of x given y. We'll make use of fact if the entropy h of x given y is 0, then x is a function of y. That is, for all y such that probability of y is greater than 0, there is only one possible value of x such that p of x comma y is greater than 0. Now the proof of that is left as homework. So if yes, that, that is the opposite direction, right? If x is a function of y, then h of x given y is 0. That we know. But if h of x given y is 0, then is x always a function of y? That we don't know. This is saying that it is always a function of y. The converse also holds. That you can write out the definition of h of x given y and then uh, try to prove it using that from the definition. But I won't prove it. So an equivalent way of saying that x is a function of y is that for all non-zero, for all values of y which occur with non-zero probability, then there's only one value of x that also occurs with non-zero probability. That is, p of x comma y is greater than 0. So in a sense, if someone gives you y, then that will automatically give you the value of x. The setup for Fano's inequality is this: you have a random variable with probability distribution p of x. You observe some other random variable y that is related to the random variable x by some conditional distribution p of y given x. Then from y we calculate a function g of y, which we denote by x hat, where x hat is an estimator of x. That is, you have a random variable x, you don't observe random variable x. You do that experiment and you observe some other related random variable y, and based on the value of y, you try to estimate what the value of x will be. And this estimate, it need not take the same value. We don't restrict it uh, to have the same values as x. So it need not take the values from the same alphabet. Now what we want to do is we want to bound the probability of error. The probability that your estimator is not equal to the random variable x. That's what Fano inequality does. And the inequality is this. It'll take it as a theorem, Fano's inequality. For any estimator x hat such that x, y, x hat forms a Markov chain. When we write x arrow, y arrow, x hat, that means x, y, x hat are in a Markov chain with PE is by definition probability that x not equal to x hat. We have h of PE plus P log mod cardinality of x is greater than or equal to h of x given x hat, which is in turn greater than or equal to h of x given y. That's the inequality. And you can make it weaker. So h of P is see, this is a binary event. Either x is equal to x hat or x is not equal to x hat. And what I mean by x is equal to x hat is that for every value script x that x takes, x hat will also take the same value. That's what it means. Uh, Only then will the two random variables be equal. They have to take for all values for which x and x hat have non-zero probability. Whenever the random variable x is equal to a particular value, x hat will also take the same value. Only then we say x is equal to x hat. Even if for one particular value in the alphabet of x, uh, x hat takes a different value in the alphabet, then x not equal to x hat. But in either case, either x is equal to x hat or x is not equal to x hat. So it's a binary random variable, uh, and the entropy is nothing but the binary entropy function that we saw in one of the previous classes. It had a form like this, right? 0, 1. At half, it took the maximum value equal to 1. So it's minus p log p minus 1 minus p log p, or log 1 minus p. So that's what h of p is. And we see from this graph that the maximum value of h of p is only 1. So 1 is greater than or equal to h of p. So we can substitute 1 in place of h of p and write 1 plus p log cardinality of x is less than or equal to h of x given x hat. Sorry, it's greater than or equal to, which in turn is greater than or equal to h of x given y. That's a slightly weakened version. From that we can write P is greater than or equal to h of x given y minus 1 divided by log of cardinality of x. This is the useful, this is the bound that we wanted. Okay, the proof for this. So this error, let me give it a name. I'll call it the random variable e. So e takes the value 1 or 0. It takes the value 1 if x hat is not equal to x. Takes the value 0 if x hat is equal to x. Then we use the chain rule to split the following entropy. H of e comma x given x hat. Given the value of your estimator random variable, what is the joint entropy between e and x? It is h of x given x hat plus h of e given x comma x hat. Another way to split it using the chain rule is h of e given x hat plus h of x given e comma x hat. Now h of e given x comma x hat is 0, because if they give you x and they give you x hat, you can tell whether x is equal to x hat or whether x is not equal to x hat. If x is equal to x hat, e is 1. If x is not equal to x hat, e is 0. So if you know both x and x hat, that if you know the value, then there is no uncertainty in the error random variable e. That's straightforward. Then h of e given x hat is less than or equal to h of e, because conditioning reduces entropy always. But what is h of p? H of e? It is summation minus summation p of p of e is equal to 1 log p of e is equal to 1 plus p of e is equal to 0 log p of e is equal to 0. But what is p of e is equal to 1? It's the same as probability that x hat not equal to x. What is probability of e is equal to 0? It's the same as probability of x hat is equal to x. But probability of x hat not equal to x, we called it PE here. So this takes probability PE. This happens with probability 1 minus PE. So the entropy of E is nothing but h of PE, which is equal to h of PE. Finally, h of x given E comma x hat can be split in two parts. This can be written as probability E is equal to 0, h of x given x hat comma E is equal to 0, plus probability of E is equal to 1, h of x given x hat comma E is equal to 1. That comes directly from the definition of a conditional entropy. Conditional entropy is the average over all values of the conditioned variable into the uh, particular conditional entropy. That is, so h of x given y was defined to be summation p of y over all values of y. H of x given y takes the particular value y. So these are particular values. It is e is equal to 1, e is equal to 0. That's what it means. So by definition, h of x given e comma x hat is probability that e is equal to 0, h of x given x hat comma e is equal to 0, plus probability e is equal to 1, h of x given x hat comma e is equal to 1. Now here again, probability of e is equal to 1 is nothing but p of e. Probability of e is equal to 0 is 1 minus p of e. What is h of x given x hat given e is equal to 0? Where e is defined as above. So given e is equal to 0, what is the entropy? What is the uncertainty in x and given x hat? Given x hat and that e is equal to 0. Yeah, so this entropy, there's no uncertainty. So this is 0. Here, given e is equal to 1, the uncertainty in x, given x hat, this we can't really tell because x and x hat take values from different scripts. So you only know that x is not equal to x hat when e is equal to 1, but you don't really know what exactly x is. So it will just remain h of x given x hat. We can't really simplify it like we did for the other case, but this is still some conditioning which will be less than or equal to h of x, right? It's But we also saw that entropy of any random variable is less than or equal to log of cardinality of script x. So we have three things here. Uh, this, and this we either evaluated or bounded them. So just substitute those things and we'll get h of x given x hat plus h of e given x comma x hat was 0. So this thing goes to 0 is equal to h of e given x hat. H of e given x hat, for now we'll forget the equality sign. We'll write h of e given x hat is h of p plus h of x given e comma x hat, which was equal to, first term went to 0, second term is p times is less than or equal to p times log mod x. So the entire thing is less than or equal to p times log mod x. Okay, so that gave us this part. Now we still have this part left. Why is that less than greater than or equal to h of x given y? For that, use the data processing inequality. It says that I of x hat is less than or equal to I of xy because x hat is a function of y. X hat is an estimator that we uh, get by manipulating y. But by definition of this mutual information, this is h of x minus h of x given x hat, which is less than or equal to h of x minus h of x given y. So we cancel out the h of x from both sides, then we multiply by minus 1, and we'll get, when we multiply by minus 1, the inequality sign changes. So h of x given x hat is greater than or equal to h of x given y. So you have this 1 and 2 combining those two equations, we get h of p plus p log mod x greater than or equal to h of x given x hat is greater than or equal to h of x given y. So that is the proof of Fano's inequality. Usefulness, like I said, you will see in applications. So to prove Shannon's inequality, you will need Fano's inequality, Shannon's theorem. But Shannon's coding theorem and Connor's coding theorem, where he tells you that, so before Shannon's theorem was there, right? People thought that people used to communicate. They still had, before Shannon also they had communication channels. They had telegraph channels, right? So they would send signals over those lines, telegraph lines. And what they thought at the time was that if you send more bits, uh, then more errors can occur, right? If you have one bit, there can be only error in that one bit. If you have 3 bits, then you can have error in we have you can have error in one of those bits, you can have error in 2 bits, you can have error in all 3 bits. So they thought that if you keep increasing the length of the sequence that you're sending, that the error will scale with the number of bits that you're trying to transmit. So transmitting long sequences will actually result in totally unreliable communication. That's what they used to think before Shannon. And Shannon came and proved that as long as you keep the coding rate below a certain value that is called the channel capacity, then you can make the error probability go to zero by using long sequences. But if you increase the code rate more than the channel capacity, then no matter what you do, you can't, the probability of error will keep increasing if you increase the number of bits that you transmit. So the converse part uses Fano's inequality. Like that, there are different inequalities where you, so the inequality itself, by itself, it's not that useful, right? It's only useful to prove other inequalities. It's like Jensen's inequality. Jensen's inequality by itself doesn't give you some useful results. But later on, when you do coding or when you find channel capacity or when you find some complexity or something, uh, or when you do some thermodynamics, something related to thermodynamics, when you are trying to prove some result, then you will use these inequalities. So one consequence here is that if the probability of error is zero, that is, if p is zero, then h of p is 0, p log mod x is 0, which implies the left hand side LHS is equal to 0, which implies h of x given y is 0. Why? It implies h of x given y less than or equal to 0, but we know that entropy is non-negative. So h of x given y is greater than or equal to 0. So from both inequalities, we can conclude that h of x given y is 0. So by p is equal to 0 means the probability uh, that x not equal to x hat, if that is 0, then uh, x is a function of y. So if x is a function of y, then you can always estimate uh, uh, x by manipulating y. Then we have corollaries from Fano's inequality. So one corollary is, suppose the estimator is just y itself. So you have x, then you observe y, and you say my x is equal to y. You say that's my estimate. And if you substitute that in Fano's inequality, we get for any two random variables x and y, let p be the probability that x not equal to y. then h of p plus p of log mod x is greater than or equal to h of x, q, and y. So that is, it's just a corollary that you're saying instead of doing any manipulation, if you simply observe something, observe a random variable and take that as your estimate, then what is the bound on the error that x is not, y is not the right estimation of x. Another corollary is let p equal to probability that x hat not equal to x, and let x hat be a function from script y to script x. That is, x hat also takes the same value as what random variable x takes. Then h of p plus p log modulus of x minus 1 is greater than or equal to h of x given y. And the proof is simple here, right? Here you couldn't say anything about h of x given x hat comma e is equal to 1. That is because we didn't know x hat could take values from completely a completely different alphabet than what x could take. So knowing x hat and that e is equal to 1 didn't give you any extra information about x. At least and directly in general we couldn't know. But if we know that x hat and x take values from the same alphabet, and we know that e is equal to 1, that is, we know that x hat x is not equal to x hat, then there are only script x minus 1 values that x can take, right? So x hat has take some value, there are only script x minus 1 values left which x can take because e is 1. So then the entropy of x will be upper bounded by log of uh, this cardinality of x minus 1. So you can replace this uh, p log mod x by p log of mod x minus 1. So if mod x is a large quantity, if, that is, if the alphabet is very large, then this doesn't impact it much. It will be approximately the same. But for small values, small alphabets, this minus 1 will give a slight reduction. So it will give a slightly better estimate. Next, we move on to the last part where we give a lemma. So this is related to kind of related to what we'll see after the problem solving sessions. Asymptotic equipartition property is the topic we will cover. So this gives you a flavor of what that will be about. If x and x hat or x dash are IID with entropy h of x. So they have the same distribution, so they will have the same entropy because the entropy depends only on the probability distribution. Then the probability that x is equal to x hat is greater than or equal to 2 power minus h of x with equality if and only if x and x hat, I say x has a uniform distribution, but since x and x hat are IID, both x and x hat have the uniform distribution. Yes, they have the same entropy, but they take different values. They might take different values. So it's like this. Um, you toss, you roll a die. Possible values of the die are 1, 2, 3, 4, 5, 6. Right? These are the outcomes. So this is the sample space. And x is the random variable, which is equal to 1 if you get an even number. If the outcome omega is even, 0 if omega is odd. X hat could be the random variable which takes 1 if W is odd. It is equal to 0 if the outcome is even. So these are two different random variables, but the probability distribution will be the same, right? So this will be, the outcome will be even with some probability p, then it will be odd with the probability 1 minus p. So here the same experiment, p and 1 minus p. So x hat takes value 1 with probability 1 minus p, but x takes value 1 with probability p. But this distribution is the same. Wait, let me check if that is. Yeah. So they, and this product distribution is the same, but the values that they're taking are different. So in this case, x is not equal to x hat. So that's what I mean when I say they're independent and identically distributed. So the distribution is the same. And since entropy depends only on the distribution, the entropies are the same. But that doesn't mean that they have to be the same random variable. They can be different random variables defined on the same alphabet. And the proof for this is, suppose x is distributed with the PMF p of x, we can use Jensen's inequality on a log function 2 power expected value of log p of x is less than or equal to expected value of 2 power log p of x. Log is to base 2. Right? Since log is a concave function. So e power log p of x is nothing but minus entropy of x, which is nothing but 2 power summation p of x log p of x is less than or equal to expected value of 2 power log 2 power log p of x base 2 is nothing but p of x, right? So the expected value is p of x times 2 power log p of x base 2, but 2 power log p of x base 2 itself is equal to p of x. So this will become summation p square of x, which is nothing but probability that x is equal to x dash. Here x belongs to the alphabet. So, like I said earlier, for two random variables to be equal, whenever this random variable takes a particular value x, this random variable also has to take the same value x. and this should be true for all values x in script x. So what is the probability that when capital X takes the value small x, capital X prime takes the value small x, that is equal to P of x is equal to x, and since they are independent, so that is equal to P of x is equal to x, and x dash is equal to x. Since they are independent, that is equal to P of x is equal to x into P of x dash is equal to x. But since they are identically distributed, this is nothing but P of x is equal to x and P of x is equal to x. So it is P square of x is equal to x. So a slight change in the previous example, when I said that they're identically distributed, they must take the same values with the same probability. So in that I said 1 with probability p, x took 1 with probability p, 0 with probability 1 minus p, and x prime took 1 with probability 1 minus p, 0 with probability p. So that's not exactly right. X prime should also take 1 with probability p and 0 with probability 1 minus p. Only then will they be identically distributed. But the way we arrive at x and x prime can be different, right? Uh, I can't think of an example directly. So, for example, if x take a fair die, that is each outcome is equally likely, then x you define it as x is a random variable which takes the value of 1 if the outcome is even, 0 if the outcome is odd. Then it will have 1 with probability uh, 1 half and 0 with probability half. Then you define another random variable x prime which takes 1 which takes the value of 1 if the outcome is less than or equal to 3, and it takes the value 0 if the outcome is greater than 3. So then again x prime is equal to 1 with probability uh, half, because 1 to 3 are equally likely, and it takes the value 0 with probability half because 4, 5, 6 are equally likely. So both random variables take 1 with probability p and 0 with probability 1 minus p, but they are not the same random variables. Now the meaning of those random variables is not the same. They are mathematically equivalent, but physically they are not, because one random variable is checking whether it's an even or odd number. Another is checking whether it's less than 3 or greater than 3. Okay, so now that's the lemma for any two random variables x and x dash with which are IID and entropy is h of x. As a corollary, we can write, so let x and x dash be independent. Let x have the distribution. So they are not identically distributed anymore, but they are still independent. Where x takes the distribution p of x, x dash takes the distribution r of x, and They belong to the same script. They take the same values. Then we can say that probability of x is equal to x dash is greater than or equal to 2 minus 2 power minus h of p minus d of p parallel r, and probability of x is equal to x dash is greater than or equal to 2 power minus h of p minus d of r parallel p. So actually this should have been the it would have been better to name this the lemma and this as the corollary, because from this you can go to this by taking identical distribution. So if you take identical distribution in this, then d of p parallel p is 0, right? Then it would reduce to probability of x equal to x dash greater than or equal to 2 power minus h of p, which is what the lemma said. But yeah, but this is how it is. It's how it was taught to me, so we'll just keep it as it is. Proof follows the same pattern. 2 power minus h of p will go from right to left, minus d of p parallel r, which is 2 sigma p of x log p of x. So d of p parallel r is p of x log summation p of x log p of x over r of x. But since you have a minus sign, I'll take that into the log and write that as summation p of x log r of x by p of x. Then summation, you group all the terms together. You'll get summation of p of x log p of x plus log of r of x, p of x log r of x by p of x. Then take the p of x common. Write this as 2 times summation p of x log p of x plus log r of x by p of x. But log a plus log b is log ab. So this is equal to log of p of x into r of x by p of x, which is nothing but log r of x. So this becomes summation p of x log r of x. Again, by Jensen's inequality, you can write this is less than or equal to summation p of x 2 power log r of x, which is equal to summation p of x r of x, which is equal to probability that x is equal to x dash. So these type of things will show up in the next chapter. This is asymptotic equipartition property. And for next 3 sessions, I will solve problems from this chapter. Everything in chapter 2 in Thomas and cover. So almost everything that we covered till now. Next 3 sessions, next Saturday, this Saturday, next Saturday, next Wednesday. Uh, all three will be problems. So problem solving session you can attend if interested, otherwise you can just see the recordings. Other things I have been uploading on the ITech the Moodle portal. Yeah, you can check. So those notes were from my professor. I can't share it on Moodle. but most of the content is there. I'm writing on the same notes, so I'll share my notes. Content is the same. The splitting is a bit different because my professor took 1 hour classes, so I am taking 1.5 hour. So uh, the content split is different, but the same content I've also covered. Um, that I will be solving problems from the textbook. Um, so maybe I'll just take a screenshot of those problems and paste it in this notes, and the solutions I'll write down, because writing down the questions will take a lot of it will just be a waste of time. So I'll take screenshots of all the questions. Do you have the textbook? If you have the textbook, then which edition do you have? Okay, let me check what edition I have. What I have is the second edition. It's not. It doesn't say Indian edition here, so it's probably the original international edition. Yeah, this is the USA print. Yeah, then I'll just post paste pictures, I guess, take screenshot and this is also Wiley. Okay, mine is just Wiley normal Wiley InterScience. This is not the Indian edition. This is printed in this is the USA edition, I think. It's okay then. I'll copy the problems. Since I'm not using it for any commercial purposes, it should be all right. Yes. Uh, what are the other chapters here? So the chapter 5 data compression I'll be covering, and then I don't think I'll do gambling and data compression. So that part won't be done. And we'll go to chapter 7. Uh, I will do, I don't know how, I'll probably be only parts of chapter 7. Yeah, parts of chapter 7, 8, 9, I think. And actually, uh, rate distortion also. Uh, yeah, there are parts of rate distortion, parts of, so it'll actually cover more chapters, but only parts of those chapters. Law of large numbers and hypothesis testing. Which section is that? So up to chapter 11, from 5 to 11, parts from each chapter. That's how many sections? Seven sections, seven chapters. So there will, but it's only parts. So it will be about, let me see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 24, 25, 26, 27, 28, 29, 30. That's about 30 hours. That'll be 20 lectures. Yeah, 20 lectures probably I won't do. I won't probably cover all 30 hours. It will depend. I wanted to cover in this course. I don't know if we'll be. I think the AEP is kind of related to. What I'll do is I'll just skip problem solving. I'll cover the theory then. Is that okay? Do you are you interested in this part only? So yeah, for you the you wouldn't be that much interested in this hypothesis testing, capacity, that type of stuff, right?
then certainly I'm interested in the